Welcome to Section 3 of Biostatistics. As a reminder, recall that we think of biostatistics in three arms. We first perform the study, then we evaluate the study quality, and then we apply the study clinically. In this lecture, we are going to be focused on evaluating the studies by talking about hypothesis testing, type 1 and type 2 errors, and confidence intervals. So let's get started.
Hypothesis testing calculates the chance that there is a true difference between two means. Another way to say this is that in hypothesis testing, you find the probability that the difference that you saw, as in the difference between the two means, was due to chance. And there are two terms you need to be very familiar with. H subscript 0, that's the null hypothesis. By default, the null hypothesis states that whatever you're presenting is false. In other words, there is no difference. And H subscript 1, the alternative hypothesis, is the hypothesis that you're presenting. To start off our discussion, let's say that our hypothesis is that daily exercise is associated with lower serum lipid levels. Now let's say after our analysis, we find that our hypothesis is true. In other words, we chose H1, the alternative hypothesis. Now when performing tests, you may have made a mistake. Perhaps we mistakenly accepted the alternative hypothesis. Maybe there really is no difference between exercise and lipid levels. And this brings us to the idea of errors.
Now there are type 1 or alpha errors and type 2 beta errors. Let's first talk about type 1 alpha errors. In type 1 or alpha errors, you incorrectly conclude that there is a difference. In other words, you accepted H1, and that's exactly what we did. Recall that our hypothesis is that there is a connection between daily exercise and lower lipid levels. This is the hypothesis we are presenting, and therefore it is H subscript 1. So since we accepted the alternative hypothesis, or H1, we want to be thinking about alpha errors. Did we make this error? The probability of making a type 1 error is represented by alpha. And it's easiest if you think of alpha as the p-value. And the p-value tells you statistical significance. And we consider things as statistically significant if you can get a p-value less than 0.05. In other words, 5%. And this corresponds to 2 standard deviations. Recall from section 1 that 1 standard deviation means that 68% of your data will fall within 1 standard deviation, while 2 standard deviations mean that 95% of your data will fall within 2 standard deviations. And 3 standard deviations indicates that 99% of your data will fall within 3 standard deviations. So when you think of this p-value of less than 5%, you should be thinking about 2 standard deviations, which is 95%. So let's go back to our hypothesis. And let's say that our p-value for this study was 0.1. This would mean that there is a 10% probability we reach this conclusion by chance alone. In other words, our chance of making an alpha error is 10%. This is universally considered too high. An acceptable p-value must be less than 0.05. Now let's do a question to apply this.
Let's say a group of non-dieting individuals is studied. The study concludes that daily aerobic exercise is associated with weight loss, with a 7% chance they reach the conclusion incorrectly. Which hypothesis was rejected, the alternative or the null? And can you find the alpha or p-value? Recall that the alternative hypothesis, H1, is the hypothesis we are presenting in the study. And in this case, the alternative hypothesis is that daily exercise, even if not dieting, is associated with weight loss. Whereas the null hypothesis, H subscript 0, by default claims that the hypothesis we are studying is wrong. In this example, the group concludes that there is an association. Therefore, they accepted H1, the alternative hypothesis. So that answers the first part of the question. The second part of the question asks us to find the alpha and the p-value. And we can find this based on the other information we were given. For example, we were told that there is a 7% chance they reach this conclusion incorrectly. So our p-value must be 0.07, and therefore our chance of making an alpha error is 0.07 as well. And recall that a p-value greater than 0.05 is unacceptable. In other words, the probability of reaching this conclusion by chance alone is too high to safely conclude that there is an association. Now let's talk about the other type of error, or type 2 beta errors. In this type of error, you claim that there is no difference. In other words, you accepted the null hypothesis, and this was a mistake. You can decrease the chance of making this mistake by increasing the sample size, n. By doing this, you will decrease your chance of making a beta error, and you will increase your power. So what is power? Well, power is the ability to detect a difference when there is a difference. So if you increase power, then you are more likely to correctly accept H1. And of course, that's assuming that H1 is the conclusion that you should be reaching. Mathematically, you find power by taking 1 minus the chance of making a beta error. So if our beta is 0.2, or 20%, then our power would be 80%. And if our beta was 0.1, or 10%, then our power would be 90%.
Now let's summarize what we learned about type 1 or alpha errors and type 2 beta errors. Remember that when you accept the null hypothesis, you should be thinking about your beta error and power. Whereas when you accept the alternative hypothesis, be thinking about an alpha error and your p-value. A helpful mnemonic is beta power and alpha p. Notice that in beta power, this O is a 0, meaning H subscript 0. So when you accept the null hypothesis, be thinking of your beta error and power. Alternatively, when you accept the alternative hypothesis, or H1, think of an alpha error and your p-value. Once again, beta power and alpha p. Now let's apply what we learned through another question. A research group hypothesized that individuals that look at a computer screen within an hour of going to bed have a harder time falling asleep. After reviewing the data at the end of the study, the group determined that there was no connection between computer screens and difficulty falling asleep. The power of the study was determined to be 0.96. Which hypothesis value did they accept? What is the chance that they made a beta error? So H subscript 1 is our alternative hypothesis, which is the one we are presenting, which is that there is a connection between looking at computer screens and having difficulty falling asleep. And as always, H subscript 0 is our null hypothesis. In this study, they rejected the alternative hypothesis. Thus, they accepted the null hypothesis. Recall our mnemonic, which is beta power and alpha p. So which part of this mnemonic are we focused on? Well, we accepted the null, which means we are thinking about this part of the mnemonic, which means we should think about the chance of making a beta error and be thinking about our power. The power in this study is 0.96, or 96%. That means that our chance of making a beta error is 0.04, or 4%, thus answering our question. Now let's talk about confidence intervals. A confidence interval tells you how confident you are that the mean will fall within a given range. The calculation for a confidence interval is the mean plus or minus the z-score times the standard error of the mean. Recall from section 1 that the z-score is simply the number of standard deviations. Also recall that the standard error of the mean is the standard deviation divided by the square root of n. And there are two basic segments to a confidence interval. There's the range, which is the calculation we just stated. An example would be 3.1 milligrams per deciliter plus or minus 1.2. Thus, the range is 1.9 to 4.3. The second segment of the confidence interval is the percent that will fall within that range. Usually, that's 95%. Recall that a 95 confidence interval should make you think of two standard deviations, indicating a p-value of 0.05, or 5%. Likewise, a 99% confidence interval is correlated to three standard deviations, which indicates a p-value of 0.01, or 1%. Basically, you have 95% confidence interval. This is the first segment. And then you have the range, which would look something like this. Now let's do a question to apply this. A study is evaluating the LDL levels in 320 FBI applicants. Results show an average LDL level of 65 with a standard deviation of 8 milligrams per deciliter. What would be the 95% confidence interval for this study? So we are looking for the 95% confidence interval. Recall the equation for confidence interval is the mean plus or minus the z-score times the standard error of the mean. And we are told in the question stem that the mean, or average, is 65 milligrams per deciliter. And recall that the z-score is the number of standard deviations we are interested in using. And we can figure this out by looking at the confidence interval we are looking at, which is 95%. Recall that 95% corresponds to 2 standard deviations. Therefore, our z-score is 2, or technically 1.96, as you recall from section 1. And the standard error of the mean is the standard deviation divided by the square root of n. So in this case, our standard deviation is 8, and the number of our data points is 320. Therefore, it's 8 divided by the square root of 320. It is highly, highly unlikely that you will ever need to find the square root of anything on your exam. Knowing where all of this information goes will get you the question correct. With that in mind, I will just give you the result here. So 65 milligrams per deciliter plus or minus 1.96 times 8 milligrams per deciliter divided by the square root of 320 equals 65 milligrams per deciliter plus or minus 0.87. This means that our 95% confidence interval is equal to 64.13 milligrams per deciliter to 65.87 milligrams per deciliter. So let's revisit this slide where we introduced confidence intervals. For simplicity, I wrote the summary of what we gained from our previous example right here. 95% confidence interval equals 65 plus or minus 0.87. Now there are 2 final facts you need to keep in mind regarding confidence intervals moving forward. So there are 2 specific situations in which you need to reject the alternative hypothesis. And these are pretty unique situations. In the first unique situation in which you may need to reject the alternative hypothesis is if the confidence interval includes 1. And this is only applicable when you are dealing with odds ratio or relative risk. We talk about relative risk and odds ratio in great detail in section 9. For now, just know that your relative risk is your risk compared to the general population. If your relative risk equals 1, there is no risk. In other words, being exposed doesn't increase your disease risk more than the general population. Now let's say your relative risk is 2. This means that you have 2 times the risk of the general population. So now let's determine if the confidence interval is significant. If your relative risk is 2, but your 95% confidence interval is 2 plus or minus 3, that means your confidence interval ranges from -1 to 5, which includes 1. Thus, you should reject the alternative hypothesis. Remember, this is only because we are dealing with odds ratio and relative risk. The next unique situation in which you may need to reject the alternative hypothesis is if the confidence interval range includes 0. And this is only applicable when you are directly comparing the difference between means. For example, if group A in your study has an average of 65 milligrams per deciliter, but group B has an average of 58 milligrams per deciliter, and you are just wanting to compare these directly, in other words, just find the difference between them, then you would find that the difference is 7, because 65 minus 58 is 7. And if your confidence interval is plus or minus 8, this would give you a range of -1 to 15, and this includes 0. Thus, you need to reject H1. Notice, however, that these 2 specific situations are very unique. In the example that we used of a confidence interval up here, which was 65 milligrams per deciliter plus or minus 0.87, this is a very typical confidence interval you are likely to see on step 1. In this example, we were not looking at relative risk or odds ratio. We were looking at an average, but we didn't subtract the averages of 2 groups, like we did in this specific unique example. In other words, just think of confidence intervals in this common application. And then just remember these two unique situations in which you may need to reject the alternative hypothesis. And that concludes the section.